talk about magnetic forces acting on a moving charge. All right, so we're going to have a part A and a part B here. Part A. We're going to do it in pictures and then we're going to do it in words, okay? Now, this is a wire, and I'm going to have current flowing in this direction. I'm trying to be all three-dimensional about this, so I have current flowing kind of away from us three-dimensionally into the page. And it's flowing at an angle theta. When I say theta, I mean an angle theta relative to the magnetic field of this bar magnet and this bar magnet. So we're sending this current carrying wire through this magnetic field. Okay, so I'm gonna draw the magnetic field so that it kind of goes above and below the wire. There we go. That's a wire ensconced in a magnetic field. How many days of the week do you get to use the word ensconced? All right. So this is actually a third right-hand rule. Maybe I'll put this in writing now. The third right-hand rule for conductors experiencing a force due to the magnetic field that they are within. If you want to use the word ensconced, you should. All right? And we say that we're inducing a force. Inducing a force as a result of flowing current in a magnetic field. And we say that it's calculated as here, we got an equation. Sorry, I was off page. The equation is force equals I times L times B times sine of theta. Oh, by gosh, by golly. That's actually a cross product. Because current is a vector and magnetic field is a vector. L is just the length of wire that finds itself within the magnetic field. And theta is the angle between the current and the magnetic field, as I just illustrated over there on the left-hand side. Okay. So we're gonna draw a right hand in just a minute, but I want to make sure that we know what we're dealing with here. I is current in amps. L is length of wire in the field. And that's just measured in meters. B is the magnetic field intensity. Now that's actually measured in Teslas. You know Nikola Tesla? It's not just a car. And that has the base units of kilogram coulombs per second, or Tesla for short. And then theta is the angle between I and B. Okay? So there's a lot going on there, and it is a cross product on top of all that. Now, if you're artistic, even if you're not, try this, okay? So here's a hand. I'm not going to make it a complicated hand. I'll make it like a nice cartoony hand. Okay? There's the pinky finger. The pinky finger of physics, okay? We're not going to try and be too complicated about this. There's our 4 fingers. There's a thumb. I know my hand looks wonky, I know. All right. Now, for this right-hand rule, what we say is that the fingers point in the direction of the magnetic field. It's like the magnetic field shoots out of the fingers. The thumb points in the direction of the current. See how my hand is trying to mimic what's going on in the illustration above? And the palm of this hand, if you're having a hard time telling which side is the palm of the hand, you can tell the fingers are bent. I'll put some knuckles on there, okay? Put some fingernails on, sure, whatever. Okay? The palm is the direction in which the wire gets pushed. Oops. Palpi, palm. Yeah. So if I run a current through a magnetic field, the wire will actually get pushed. It's a motion thing. It's a force thing. And that kind of makes sense. That if this wire has its own right-hand rule of magnetic field around it, that its magnetic field is going to interact with the magnetic field of the bar magnets. And it actually causes a push. You know, magnets affect other magnets. In this case, just a straight wire is being affected by other magnets. We're going to have to come back to this next time. This is as far as we're going to go. And we'll come back to talk about what happens when it's not just a simple wire, but a charged particle flying through a magnetic field. Oh!